Today we are looking at the paper Learning to Discover at Test Time by Mert Yuksekhanol, Daniel Koseja, and the teams at Stanford and NVIDIA.
Right, and this is a really fascinating one. We're going to get into a technical breakdown of their method, which they call TTT-Discover.
The core hook, I think, is that they're moving way beyond just prompting frozen LLMs. So you can forget about chain of thought or, your standard best event.
Yeah, this is a whole different level. They're performing reinforcement learning RL during inference on the specific test problem itself.
Which is just a huge shift.
It's a fundamental shift because TTT-Discover isn't optimizing for average policy performance. It's built to find a single outlier solution, the discovery.
And it does this with a couple of new mechanisms, right?
Two novel components. First, there's an entropic objective that basically forces the model to overfit to the best solutions it finds.
Okay.
And second, there's a PUCT-based reuse strategy. It's a bit like AlphaZero, but it's modified to chase the maximum potential reward, not the average one.
And the results, they really speak for themselves. Using an open model, GPT-OS 120B, and just applying Lorai updates at test time, they got SOTA results all over the place.
All over. In math, they beat AlphaVolve on the Erdős minimum overlap problem.
In systems, which is wild, they beat human experts by 50% on A100 GPU kernel optimization.
They also won retrospective AtCoder contests and hit SOTA on single-cell RNA sequencing in biology.
And what's the cost for one of these runs?
That's the kicker. It's roughly $500 per problem to get these kinds of breakthrough results.
All right, so that's the 1-minute summary. Now let's really dig in, because this paper, it feels like it's attacking the entire current paradigm of test time scaling.
It is, yeah. Right now, when you hear test time compute, you're almost always thinking about search.
Right. Tree of thoughts, best event, maybe some evolutionary stuff.
Exactly, like AlphaVolve. But the model itself is frozen. The weights of the neural net, they never change.
Which means the model isn't really learning anything from its mistakes during that search process.
It can't. The authors have this great analogy for it. It's like a student taking a ridiculously hard exam, something that needs a spark of genius.
Okay.
With a frozen model, that student tries a solution, fails, and maybe keeps that failure in their short-term memory. That's the context window.
But their brain, the actual neural weights, it's not changing.
Precisely. They aren't getting smarter. They're just guessing, but with a scratch pad.
Whereas TTT-Discover is basically letting the student cram for the exam during the exam.
Yes, using its own failed attempts as the study guide. They lean really heavily on the bitter lesson here.
The idea that general methods just scale better.
Right. History has shown that general methods like learning and search just scale better than handcrafted human heuristics. And their argument is, well, why stop at search?
If you have the compute.
If you have the compute, why not actually update the model's parameters to adapt to the specific problem you're trying to solve?
So let's talk about the implementation. They can't be doing full fine-tuning. That would be way too slow.
Oh, no way. They use low-rank adaptation, LoRa, specifically rank 32 updates.
Okay, so it's efficient.
Right. And they treat the rollout data, all those failed attempts from the search, as a kind of dynamic on-the-fly beta set. So for each problem, you're training a little specialized LoRa array adapter just for that instance.
But they make a point to call this discovery RL, not standard reinforcement learning. What's the mathematical difference there?
It really boils down to the objective function. Standard RL is built to maximize expected reward.
You want a policy that's robust, that works on average.
Exactly. You want a self-driving car that doesn't crash 99.99% of the time. You optimize for the average.
But for these discovery problems, like finding a new math proof, you don't care about the average at all.
Not one bit. You don't care if the policy collapses or if it overfits so badly it forgets how to do anything else. You only need to find one single valid state that beats the current best.
It's a needle in a haystack problem.
It is, not a drive safely problem.
So how do they change the objective function to encourage that kind of, risky behavior?
They use what they call an entropic objective. So instead of just maximizing the expected return, they exponentially weight the probabilities of the highest reward trajectories.
I saw the formula for this. It has that beta parameter, the Greek letter beta, as the exponent.
Right, and if you crank that beta way up, the model essentially starts to ignore all the low reward paths and just focuses laser-like on the peaks. It gets incredibly greedy for that one outlier.
But doesn't that just lead to immediate collapse? If you just tell a model, only look at the best thing you've ever seen, doesn't it just get stuck?
It would, yeah. which is why they have to constrain it. They make that beta parameter adaptive, and then they bound the updates with a KL divergence budget.
Okay, so it can't stray too far from the original model.
Exactly. It's very similar to relative entropy policy search, or REPS. It keeps the updated policy inside a trust region, so it doesn't just start spitting out garbage, but it's still pushing aggressively toward those high reward spots.
Okay, so that's the learning part, the weight updates.
Yeah.
But there's also the search structure, this reuse component.
Right, and this is to solve the horizon problem. An LLM, even with chain of thought, it can only think so many steps ahead in one go.
Its reasoning horizon is finite.
Totally. So TTT-Discover keeps a buffer of past states, basically partial solutions it's found.
And it starts new attempts from that buffer.
Yes, but not just randomly. It uses a modified version of PUCT that's predictor plus upper confidence bound applied to trees. It's the same search algorithm from AlphaZero.
But they changed the scoring rule, didn't they?
They changed it in a really important way. Standard PUCT scores a node based on the mean value of its children. It's risk-averse.
It wants the average good path.
Right. But TTT-Discover, in keeping with this whole discovery RL theme, scores a node based on the maximum value of its children.
Wow, that's incredibly optimistic.
It is. It's basically saying, I don't care if 99 paths from this node led to a dead end. If one path led to a breakthrough, this is a great node to explore.
And that lets it build these super deep solutions.
It extends the planning horizon almost indefinitely. It lets the model stitch together solutions that are thousands of steps long, way, way beyond what you could ever fit in a context window.
Let's move to the applications, because this is where the rubber meets the road. The systems engineering one, optimizing GPU kernels, really jumped out at me.
Oh yeah, the TriMul task. Triangular matrix multiplication. This is a super important kernel for things like AlphaFold. They basically gave GPT-OS120B the task of writing Triton code to optimize it.
And the benchmark was actual human expert.
A leaderboard of them, yeah. For the A100 GPU, the best human submission ran in about 4,500 microseconds.
And the model.
The TTT-Discover kernel hit 2,198 microseconds.
Wait, so it's a 50% reduction in latency? That's insane. In kernel engineering, you fight for a few percentage points. How did it find that much room for improvement?
It's so fascinating. It really shows the gap between human intuition and what a machine can discover. The human experts all treated it as a compute-bound problem. They focused on the matrix math.
But that wasn't the real bottleneck.
No. The AI figured out that because of all the element-wise operations like layer norm and sigmoid gating, the problem was actually memory-bound.
So it optimized for memory bandwidth, not just FLOPs.
It performed this massive fusion operation. It fused the input layer norm, the gating, and the output layer norm all into a single kernel to minimize reads and writes to global memory.
That's a clever move.
And then, this is the real senior engineer part. It converted the inputs to FP16 and just delegated the heavy and $3 Entrix multiplication to kubeless.
So it knew when to write its own code and when to call the library that's already hyper-optimized.
Exactly. It didn't try to beat NVIDIA at their own game. It beat the humans at memory management. And these results held up across the H100, B200, MI300X. It generalized.
That generalization is so key. It wasn't just overfitting to one chip's weird cache. Okay, so now let's jump to the math domain, the Erdős minimum overlap problem.
A classic problem in combinatorial number theory. The previous state-of-the-art was held by AlphaVolve, that evolutionary search method.
And before that, human mathematicians, I assume.
Right. And this is where you see the bias problem so clearly. Both the humans and AlphaVolve, they all found symmetric solutions. Their constructions were neat, clean, symmetric step functions.
Because symmetry is a powerful heuristic. It simplifies the search space.
It's what we're trained to look for. But TTT-Discover doesn't have that training. It just cares about the reward signal. And it found a construction with a lower overlap constant, beating the previous best.
And what did the solution look like?
It looked completely different. It was a 600-piece asymmetric step function. It was messy, complex, and totally counterintuitive.
So it broke the symmetry constraint because it was never told to look for symmetry in the first place.
Exactly. It's the bitter lesson all over again. We think the solution should be elegant and beautiful. The model just finds what works.
They also mentioned another bad problem. Autocorrelation inequalities.
Yeah, finding the minimal autocorrelation of binary sequences. There, TTT-Discover found a 30,000-piece step function to set a new upper bound. But the coolest part was the agentic behavior it showed.
What do you mean by that?
Well, the model started its search using gradient-based optimization. But as it got a feel for the problem's landscape, it switched its strategy entirely.
It changed algorithms mid-run.
It started outputting linear programming formulations. It realized that to get that last bit of performance, it needed to solve for specific constraints. It learned a pruning strategy on its own, focused only on the tight constraints, and then framed that as an LP problem for an external solver.
Wow. That's a level of meta-reasoning that goes way beyond just predicting the next token. It's tool use.
We saw that in the competitive programming tasks, too. They ran it on some past AtCoder contests.
Right, these are like optimization problems dressed up as games.
Exactly. And TTT-Discover would have placed first in both of the ones they tried, beating all of the human contestants. And for one of them, it didn't just write a simple script. It implemented a full simulated annealing algorithm with beam search in C++ prevent.
So it wrote a sophisticated search algorithm as part of its own search process.
It's recursive search, yeah. It beat other specialized agents like ALE Agent and Shinka Evolve at their own game.
And what about the biology application? Single-cell RNA sequencing.
A denoising task. You get this really sparse, noisy data from single-cell reads, and the goal is to reconstruct the gene expression. They use a standard benchmark for this.
Did it start from scratch on that one?
No, and I think that's a really important detail. They initialized its buffer with the code for an existing algorithm called Magic.
So it was like refactoring someone else's code?
Pretty much. It took that standard code base and just iteratively improved it. It added things like gene adaptive transform ensembling and a low-rank SVD refinement step. It took a standard tool and engineered it into a new SOTA solution.
Okay, I really want to talk about the ablation studies.
Yeah.
Because we need to understand why this works so much better than the alternatives. Like, why not just sample 1,000,000 times with best of n?
They tested that. And, best of n does improve performance over a single shot. Of course it does. If you buy more lottery tickets, your odds get better.
But it plateaus.
It plateaus hard. You look at the graphs in the paper, and best of n just flattens out way, way before it reaches the solution quality that TTT gets to.
Because it's just rolling the dice over and over. It's not learning.
Exactly. It has no mechanism to lock in what it's learned. TTT-Discover uses the LoRa weights to actually remember the path to those high reward regions. They also compared it against what they called naive RL, just standard expected reward optimization.
And that didn't work.
It failed completely. Naive RL is just too conservative for this. It's designed to keep the policy safe and stable. For discovery, you need that entropic objective to force it to take risks and chase the outliers.
What about the comparison to theta evolve? That's another method that updates parameters.
Right. Theta evolve uses evolutionary strategies to update prompts or soft prompts, but TTT-Discover, using the same compute budget and the same base model, just blew it out of the water.
Which suggests?
It suggests that gradient-based learning, actually following the gradient of the loss function, is just fundamentally more efficient than these evolutionary heuristics, at least for these kinds of high-dimensional language problems.
Okay, let's talk about the elephant in the room with any kind of test time training, which is cost. Inference is supposed to be cheap.
Well, they report an average cost of about $500 per problem.
$500.
Which, for a consumer app, is obviously insane. You're not spending $500 to summarize an email, but you have to look at the value proposition.
Right.
A 50% speed up on a GPU kernel that's going to run on every H100 in a massive NVIDIA cluster. That's going to save you millions of dollars in compute and electricity.
Or discovering a new mathematical proof.
What's the price on that? For these discovery class problems, $500 is nothing. We're really shifting from inference as retrieval to inference as R&D.
It really blurs the lines we've always used. We think of pre-training as learning and inference as just applying that learning.
His paper just says inference is. Well, it's more learning.
The distinction just kind of disappears.
I think for these really hard problems, it should disappear. We might be heading toward a future where you have a generalist base model, and for any specific hard task, you just spin up a specialist instance that trains itself on that one problem for, say, 12 hours, solves it, and then you just throw it away.
A disposable expert.
Or you keep the lower weights, you archive the specialist, and if you ever see that problem again, you just load the adapter.
And all of this was done with GPT-OS 120B, which is a very capable open model, but it's not a frontier model like a GPT-4o or a Claude 3.5.
And that, I think, is the most provocative part of this whole paper. They beat humans and they beat closed frontier models by using an open weight model and just trading compute for test time learning.
So the final question is, what happens when you apply TTT-Discover to a frontier model?
If the scaling laws that we see in pre-training also apply to test time training, and this paper really suggests they do, then applying this method to a GPT-5 class model could unlock things we currently think are years away.
We might just be underestimating what our current models are capable of if we just gave them a chance to study for the test.
It feels like the bitter lesson isn't just about the quantity of compute, but about where we choose to apply it. And shifting more of it from pre-training to inference seems to be the next frontier.
Absolutely. The budget for inference on these hard problems is about to go way, way up, and papers like this are showing exactly why that's a smart bet.
We'll have a link to the paper Learning to Discover at Test Time in the description. It's a dense read, but if you're working in agentic workflows or systems optimization, you really have to check it out.
Highly recommended. Thanks for tuning into this deep dive into the technical side of AI. We'll catch you on the next one.